A ray of light traversing the surface, separating two mediums of different density, is refracted, that is, deviated. But light is composed of various colours, and the angle at which the colours are refracted differs for each of them. For this reason, in a positive lens, the light rays do not all converge exactly at the same point, but the radiations of shorter wavelength focalize closer to the lens and those of longer wavelength further away from it. This phenomenon is known as chromatic aberration. The lack of a single focal point provokes a phenomenon of iridescence, which significantly impairs the quality of the images. Already the first telescope makers had empirically realized that the effects of chromatic aberration in a telescope substantially diminished when the ratio between the focal length and the diameter of the objective was increased. 17th century telescopes, in fact, not only had relatively long focal lengths, but were also usually fitted with a diaphragm to reduce the aperture. But the focal length required to limit the effects of chromatic aberration is not proportional to the diameter of the objective, but to its square. If, for example, an objective with aperture of 2 centimeters shows no appreciable chromatic aberration for focal lengths of at least 75 centimeters, an objective having double the diameter, i.e. 4 centimeters, must have a focal length 4 times greater, or nearly 3 meters. This circumstance profoundly conditioned the subsequent evolution of the telescope. On the one hand, progressive increase in the diameter of the objectives led to the construction of increasingly longer telescopes, to the point of reaching the practical limits of fabrication. On the other, it stimulated the search for solutions based on the utilization of mirrors, which, working by reflection, are not affected by chromatic aberration. A concave mirror focuses the rays of light exactly like a converging lens, and can thus be utilized as objective. In 1663, the Scottish mathematician James Gregory proposed an instrument consisting of a main parabolic mirror and an elliptical secondary one, which sent the optical beam back behind the primary mirror, which had a hole in it. The Gregorian reflecting telescope, which furnishes erect images, met with great success in the 18th century, thanks above all to the famous Scottish optician James Short. In 1668, Isaac Newton designed a telescope in which a plane mirror of elliptical shape, inclined by 45 degrees, reflected the optical beam laterally, outside of the tube, where the eyepiece was positioned. A second version, still existing today, was presented to the Royal Society in 1672. In that same year, the Frenchman Laurent Cassegrain proposed an instrument in which the secondary mirror, a convex hyperbolic one, was placed in front of the focus of the primary, focusing the image, as in Gregory's telescope, in back of the latter. The first truly efficient reflecting telescope was a Newtonian one, with a 6-inch aperture presented in 1721 to the Royal Society by the Englishman John Hadley. Its performance equalled that of Huygens' refracting telescope, 123 feet long. Although reflecting telescopes of large size were built during the 17th century, the poor reflecting power of the mirrors of the time, made of a copper and tin alloy called speculum, that reflected only about 60% of the incident light, prevented the success of the reflecting telescope. The problem was solved in 1856, when Léon Foucault and Karl August von Steinheil invented the process of silver plating that allowed the utilization of mirrors made of glass, covered with a very fine layer of the purest silver.